Hello everyone and welcome back to the channel. I'm very glad to see you here. And this is the continuation of the memflow apply series. What we're gonna do in this episode, well, glad you asked, we're actually gonna work on something called pointer map. And just to recap, in the previous episode, we extended our value scanner, and if you have a structs binary, you have, for instance, the money value right here, 97. If you run it, if you scan for I6497, you're gonna have 23 matches. And when you lower to 94 and just type in 94, you're gonna have that one single match for the money. And just to prove it to you, I'm gonna make it go down to 92. And if we print it out with P command, we're gonna have this go down to 92, which means it's our actual money value. So in this episode, what we're gonna do is work on something called pointer scanner. And this is a very similar concept to value scanner, but instead of searching for values, we search for valid pointers. And why do we want to do that? Well, our final goal is a offset scanner so that you find the values, you find what you're looking for, and then it creates offsets that you need to use to do reference values to get from point A to the value B in case the game updates or something. When the game updates, all the file offsets are gonna get scrambled. You will need to find them again. And the offset scanner, what it does, we will be able to start from some really well-known location, like a snippet of code that's not gonna change in an update. From that snippet of code, it's gonna go down and down and down and down and down with some certain offsets down to the value we looked for. And once we find the value we look for, then we are able to replace it or read it or whatever. And by having that offset tree, we will be able to have our programs still work after updates occur. And to do that, we're gonna use a so-called pointer map. Pointer map, we just find the pointers, we find those links. We find those links between different addresses. And when we find those links, we're able to just search through those links and find those particular offsets very efficiently. And that is exactly what Cheat Engine does. Inside it's like pointer scanner, structure offset builder or something like that. It does exactly that. And we're gonna do that here in Rust in very concise code, and it's gonna be very beautiful. So without anything further to do, well, actually there's one more thing to do, and that is overflowing that like button. Seriously guys, just overflow that like button. It's gonna help me tremendously. Your support is incredible, and it's always been incredible, and that like button, it keeps me going and keeps me making better and better videos. So do that. Thank you tremendously, and now let's get started. So what we're gonna do, I will first show you the changes in structs binary. And the changes in the structs binary are rather simple. So right here you can see when we print the state, we're printing the address of the state. And we're also inside state and account, we print their addresses. So it's really simple. What we did here, right here, out of this code, we get the GS, which is of reference mutex. It's really important to specify that we're looking for a mutex, because using lazy static, the initial variable is called global state of type global state, which actually doesn't point anywhere. It's very useless by itself. So we just specify that we want the inner value, that is the mutex. And we get a pointer and we print it, and it's all good. And inside of the tick function, we print state, and we just print the pointer to it. And inside the do operation, we print self-cast to pointer, and we instead hold the box to state because it adds an extra level of indirection, and you're gonna see how cool is that once the pointer scanner is working. Now let's go to scanflow, and we're gonna do it. We're gonna create a module called pointer map, which will be a rather simple module. It's just gonna be a structure, pointer map, which is gonna hold a map of pointers, which is a B-tree map. And B-tree map is a Rust collection for a map structure, and we need to import it. Use SD collections B tree map. And B tree map of two types. Single pointer points to another pointer, so it's address to address. You have one address pointing to another address, and you may have multiple addresses pointing to the same address. Be wary of that. That is really, really important thing to note when we will be building backwards a finding of the references. It's gonna be pretty awesome, I have to say. So you have address pointing to an address, and that will be it pretty much. And we just implement pointer map. We add a reset function, and it's going to be self.map.clear. We're gonna have a create map function, which takes a virtual memory object. If we type add value scanner, it's gonna be very similar to this function. Actually, let's just copy it. And the difference is it's called create map, and it's gonna take memory, and it's instead of data, it's gonna take a pointer size, like size address. And what we're gonna do here is, first of all, create the memory map. And it's gonna be the same thing, really. Let mem map equals that. One could argue we might wanna just use the memory map from value scanner, but let's keep it decoupled. We might merge them in later on, but for now, no need, I'd say. And the same buffer equals vector of 0, one single page with size address -1. Just one single page with a little bit overshoot allowed. In general, pointers are mostly gonna be aligned to the size of it. So it's gonna be every 4 bytes on a 32-bit machine or every 8 bytes on a 64-bit machine. But I mean, let's not give things to chance. Let's have like pointers allowed to be misaligned. It's gonna make things really good, I'd say, if we were to do that. And what we're gonna do is, well, have pretty much the same loop right here. I'm not gonna lie, it's gonna be very much the same. We take 6 lines and we're just gonna delete that. Here we go, them. So yeah, we perform the reads, we go through the mem map and read all those regions one by one. And what becomes interesting is the inside part. Now, instead of searching from data length, we go by size address. And we're also gonna go and do is create an address equals address plus off plus O. So we have the address, we first offset by this amount, which is stepped by one single page, and then we within that page we offset by O, and that will be our final address. And we're gonna create an array because we have this buffer and we need to convert it to an address, but we can't go directly because on 32-bit machines that buffer is gonna be 4 bytes. So we want to take those 4 bytes and then convert them to an address. So what we're gonna do is create array which is of 0 and length 8, which we're gonna then convert to U64 and then U64 over to, you know, the address. And that's gonna be, we're gonna just copy out to, or like above.len, copy from slice. Yeah, if we copy from slice, and this is only gonna work on little Endian. We do looks for big Endian. Little Endian and big Endian are just different ways how numbers are built. On little Endian, the smallest values are at the very start and then it grows to the right. So if you have a 64-bit integer and want to go up to 128-bit integer, the address is gonna be the same. All you have to do is allow for more space at the end. On big Endian, it's pretty much swapped around, and we need to instead copy to the end of the buffer and then convert it to that. But big Endian is very rare, actually. Like, to be honest, big Endian is long dead and nobody's using big Endian, so it's not really a big challenge anymore. So you can just assume it's a little Endian machine. So out address equals address from, and you're gonna have U64 from little Endian bytes. Here we go. And now we're just gonna import all the things. We're using types. We're using size and address. We're using virtual memory and virtual redata. And yeah. And if we go to main, and if we start using pointer map, and we're using pointer map. Here we go. If we run it, we're gonna have errors because we actually need to return something right here, and that will be an OK of nothing, unknown field. Yeah, instead of going through self memory map, we're actually not storing the memory map. We're going just to the memory map, which is right here. And one more error. Yes, it has to be pointer map, not pointer map. Pointer map. All right, so things do be working. Why don't we add a command called pm pointer map or pm? And what it's gonna do is gonna create a pointer map. Shocking, I know. Pointer map equals. We're gonna create a default one, which we derive it? No, we don't derive it. We have the default one, and what we're gonna do is this gonna work? Yes, it's gonna work. It's gonna be mutable. We're gonna do pointer map dot create map. We're gonna take in a memory and size address. It will be process.virtmem, and size address is gonna be process info dot size address. Oh wait, no, info. We try process architecture and then size address. I'd say that should work. Aha, it works. And if we type in PM, we have things happening. Look how fast it is. Although we kind of don't have it. Like, hold on. We actually don't like print anything. I'm not sure if it works. So we're gonna do map size, and it's gonna be self dot. All right, we actually. We're not actually doing anything, right? Of course we're not. So what we need to do here is, instead of looking for a particular value, we're looking for a address which points to a valid memory region. So that means we're looking for an address which points somewhere within the memory map. And how are we gonna do it? Well, we've got the out address. All we have to do is search through the memory map and see if it's within the memory map. So it's going to be very easy. Use the binary search function, map.binary search by. And binary search by is just going to create a binary search over the memory mapping using a custom comparison function. And it's just going to be AS. And here, it's going to be the same address and size. And we're going to return equals if the out address is within here. So if more or equal to A and out address is less than A plus S, then we return ordering equal, else return no. Else just compare the starting addresses because we already know it's not within, so it's either greater or less. So it's going to be very simple. A.compare out address, and that's it. And we just check in the if statement right here, we just check if it is okay. And if it's okay, we're going to do map.insert address. This particular address points to this particular address. And we need this. And we also need to import add ADDR. Here we go. Now we've got a high number of pointers. And we got actually roughly 32,000 pointers, which is quite an okay number for this tiny application which we have. So now we finished the pointer map, but it's kind of difficult to visualize it and know what it does without actually implementing the search function. So we're not actually gonna do the searching. Instead, we're gonna create a function which is gonna take an input address and then it's gonna go down the pointer map, go down it, and just print one level deeper and print all the pointers within, and we're gonna find all sorts of addresses we're interested in. So we're gonna start from this particular address right here, 4F8040, and we're gonna go down and we're hopefully gonna see something very close to the money value. It's gonna be something very close to BOF8C8, somewhere within that pointer map, which we will print out. So how do we actually do it? Well, let's just build a really simple function. It's just gonna do what we're gonna call it. It's gonna walk down range. Why range? Well, we take a self, we take an address, and we take a range of from the starting address, lower range, which is how far below the address we're willing to go. And we're also gonna take an upper range, which is how far beyond that input address we're gonna search for pointers in. We're gonna get which level we currently are at, and we're gonna take a max levels, so we don't just go and search for things infinitely. In case there's some circular thing, it would make the search infinite, and we don't want that to happen. So max levels, gonna take an EU size, and what we're gonna do is create a min. We would need to do address minus L range, which actually could work. Honestly, it could work. The issue is we don't really want to wrap below null pointer if it is a null pointer. So we're going to use address from, and it's going to take address as U64, and we're going to use saturating sub L range as usize, as U64 or whatever. What we did here is instead of subtracting from address the lower range, we use a saturating subtraction, which is basically gonna say if it reaches 0, it's not gonna overflow back. So this is the type of thing we gotta be very careful in terms of like buttons, because we want to overflow them. But if they were to use the saturating add function, it's gonna reach the top number and not overflow. And this is really, really important. And here we're actually not interested in overflowing. So we use the saturating function. And the same thing for max. It's gonna be address from address as U64, saturating add, and the upper range as figure out the type, and usually takes only one thing, that is U64, and it's gonna cast it to U64, which will never overflow really. Now we're just gonna print out the indentation level. We're gonna be very simple. It's just gonna be in 0 level. From 0 to level, we're gonna print, not print line, but print 4 thingies, an arrow like this. Something like that will work, and we're gonna print the line like this. I don't know, and it's gonna be address. So now we reach the point where we need to search the B-tree map for a particular range, which is from minimum to the maximum. And how do we do that? It's really, really cool actually. B-tree map is a binary search tree, so you could use the properties of the binary search tree to extract a range really, really effectively. And this is what we're gonna do. Watch out, it's not actually a binary tree. It's a B-tree with like 6 things on each node. An implementation detail which increases efficiency, but we shouldn't worry much about it. It's a really efficient tree structure. So what we're gonna do is we're gonna use a so-called self.map.range function. So we're gonna use the key and the value in self.map.range. And range is defined for like regular numbers is from like 0 to whatever. In our case, it's actually not gonna work. We're gonna use a so-called tuple, which is gonna take included min and included max. And these are coming from use std_obs bound included. And here we go. We're missing things. Yeah, we are missing something. Here we go. This should work now. It compiles. And now what we need to do is do the same thing for each level. Just go like this. We could actually just do this here. And here we use the regular old arrow. And we're gonna do if, and now we're gonna print the offset. And this is gonna be, so the key is the starting address and value is the address it's pointing at. So we're gonna compare. We actually can borrow these. If k is less than address, we're gonna print minus offset because k is less than address, so it's gonna be minus something. And it's gonna be minus address minus k. Else, it's gonna be a plus offset and plus k minus address. And then we're gonna print the line of the actual value, which is k points to something, k to value. And if the level is less than max levels, we're gonna recurse downwards and we're gonna call self dot walk down range. Instead of the address, we're gonna use the value points at instead of the key, the value we're starting from. So we take the value, we take the same L range, same upper range, and we're gonna take current level plus 1 and max levels. Let's see. Expected tuple. Oh, we need to borrow it differently. Here we go. It works. The pointer map, we're gonna do pointer map dot walk down range 0, 16. Let's not go into negative offsets because we know our structures are always going to positive offsets. So we don't go into negative side, but we go into positive side by 16 bytes. And we start from level 0 and we go like up to 5 levels deep, let's say. And the address equals, well, for instance, this one. We're gonna take this one and convert it. And let's just run it. And let's see. So let's first find our value. So we have money 101, I64 101, oops, reset, I64 101. We find loss of 101 values. We go to 99. We have the BOF 8C8. And just note, we start from here. Our state is here and our account is here. And we're just gonna take it PM. And we have our pointer map. So the first one, it doesn't seem to point to actual right value because our state is BO55. This is BO52. So we ignore it. We go down to here, which is plus 10. It is 4F8050 points to BO55D0, which is our state. And we have our state plus 8 points to BOF8B0, which is our account. And in the account, aren't we looking for our money value? So if we just print, we have BOF8C8, we point to this one, plus B0, and we have C8, which is gonna be 0x18, which is, I'd say, very much within what we're looking for. And for instance, if we reset this and we search for str Jeff Ori, you're gonna have a BO55F0, which is right over here at offset 0. You've got a pointer to BO55F0. And I have to say, isn't that cool? That you've got the string match to Jeff Ori and it's in like the same pointer map. We go here, and right here at this one, you're already inside the structure, which is, you know, all this stuff. You've got the offset 0 pointing to our string. You've got offset 0x18 pointing to our money value, and so on and so forth. Basically, I have to say it's pretty cool, and I say we absolutely nailed it. Thank you very much for watching. This was pretty much it. So to just recap what we did, we added a pointer map command, which creates a pointer map, which is basically same as value scanner, but instead of searching for values, we search for valid pointers. basically for address values which are within the memory map. We find if it's a value within the memory map, we insert it into the pointer map. And we've got a map of particular size of 30,000. And then what we added in the pointer map command, it's created the map and it walked down at the particular address, which we will later learn to find. The root of our global state is this particular address, and we walk down it and we print out all the different pointers which are very close within. You can see the first one points to some. It's actually a mutex, so it points to some internal mutex structure. It's not relevant for us, but what's relevant to us is the plus 0x10 offset, which points to our beloved state, which then has a pointer to our account, which is right here. And then once the account is done, well, you are pretty close to the money value. So yeah, thank you very much for watching. This was pointer mapping. In the next video, we will actually go into code analysis, which will allow us to directly find all these addresses within the code, which will be valid for our searching. And once we have that stuff in, it's gonna be really, really cool. We're gonna have a really feature-rich scanner. And once you've got the scanner, you will be able to build offsets, and we will be able to then build patterns and stuff like that. It's gonna be cool. It's gonna be cool. Thank you very much for watching. Thank you for posting comments. Honestly, it's really, really cool to read all your comments. You know, I respond to all of them, and pop them down what you think of this video. If you have any suggestions, I'd love to hear them. Next video is gonna be awesome, and I suppose I will see you then. Thank you very much for watching once again. My name was Heap. Yours wasn't defined. See ya.